Well, potentially there was incredible discussion that got missed. All right, falling through a hole. Pardon? Falling through a hole. Now, it might seem like an odd thing to throw in at this point, but we're going to do it anyway, because it will connect. So basically, Earth, hole, straight through the middle. We're not dealing with the feasibility of can you actually do that. We're just assuming it can be done. And so you got a person on one end, and he's going to step through the hole, and he's going to fall. I'm going to make the assumption that the Earth is round. That it is a sphere, so Earth is a sphere. I'm going to make the assumption that the mass of the Earth did not change when we dug the hole. Not appreciably. So the mass is still about 5.98 times 10 to the 24th kilograms. Because the Earth is a sphere, there is a set radius, and so the radius of the Earth, which I'll label as a capital R, is 6.38 times 10 to the 6th meters. And I'm going to assume the density of the Earth is uniform. Probably of all the assumptions, I think that last one's probably the weakest of the assumptions. Because we know we've got a crust up here, and then underneath that we got the plasma.
What's the little symbol you got there for the density?
That's a rho. The Greek letter rho. And that's the symbol for density. I forget what your textbook uses. It'd be nice if I could just tailor each lesson to what the symbols your author uses, but at some point it just like started losing track of which book did which. So standard symbol for density is the letter rho. Although some use the letter D for whatever reason, like there's a connection. So we got it, there's if I have spherical symmetry in the density. So the fact that density is uniform satisfies this, but the next bit just requires that I've got some sort of spherical symmetry of density. So I can have layers just so long as the same distance from the center of the Earth has the exact same density. Then the force due to gravity on an object equals the force due to gravity from the mass within, actually let me throw some extra words in here. The force of gravity on an object a distance r from the center, that's a lowercase r, is equal to the force of gravity from the mass within a distance, lowercase r of the center. This can be shown given an hour and some calculus, which I will not subject you to. So when the person is here, so when the person is at this point, so a distance r, lowercase r away, the force due to gravity is the force due to gravity from basically a sphere that size. We don't need to worry about the mass that's farther away from the center than he is. If you took Physics 251, we can go through the derivation. If you're interested, I can also post the video where I go through the derivation. It is as exciting as you would expect. actually, there's something that's kind of neat that you go through this huge, long derivation, you get a lot of letters all over the board, and in the end, you get 0. As in the force due to gravity from all this stuff out here. It's what I like is the simplicity of the answer, given how complex everything else is. Some students find it frustrating that you go through all that and you end up with just 0. So, force due to gravity. Let's see if dredge that one up from the past. I'm not talking mg, I'm talking the more generalized form of it. Anyone happen to remember the more generalized formula for the force due to gravity?
I know that.
I'm getting a lot of waiting for someone else to answer it. 5-0. Your expression, Nick, is I'm satisfied with his doing it.
It's been a while.
Yeah, it's
Yeah.
been a long time, I'm sorry. It's the gravitational constant over,
Velocity?
no, it's,
How fast an object is going?
you need to know the mass of both objects
Okay, yeah, so mass 1, mass 2,
and the radius, divided by the radius,
squared.
squared, right?
I would still contend that finding this value of g here, it's got to be one of the most tedious physics experiments ever. Now, we might challenge that with some of the experiments that you're going to do this semester, but the precision, because the force due to gravity between two small masses is not particularly big. There's a force of gravity between you and every object in here. But it's not like you have difficulty walking out of the room. It's not like you're being pulled back physically, just emotionally. So as you're walking out the door, that gravitational force is small. So just imagine you're trying to set up an experiment to find this value of g is you take these two masses and you put them a set distance apart. And then you see how much they affect each other.
It must be riveting.
Yeah, you would have to have some patron who's going to basically be paying for everything, because you would have, I'm just imagining the weeks. You finally get it set up, and then a horse and buggy goes by and the room shakes a little bit, throw in and completely off. So now you have to wait for everything to get still again to conduct your experiment. Then your kid runs into the room, slams the door. Now you have to wait for it to get all quiet again. And speaking of cruelty humor, the Egyptian who figured out the radius of the earth based upon the sun's shadow, he has to do it on the solstice. And I'm just picturing he had the stick set up, he had it perfectly lined up, and it was a cloudy day. Or just as he needed to take the measurement, the stick fell over. Potentially he got it right the first time, I don't know. They don't talk about how long it took them to actually get that experiment right.
How big was the stick that he was using?
I always pictured it as a stick like this big. I don't know, were you picturing something taller?
I don't know how you use a stick in the sun to find it.
He put two sticks, like several hundred kilometers apart. That's how he was able to figure it out. One in, I think, one in the Roman Empire and the other end of the Roman Empire. I don't know exactly how far.
I always pictured them closer than that, but
Yeah,
yeah.
they were very far away. I know that they were like hundreds of kilometers, I'm pretty sure.
I mean, more power to him that he had the patience to do it, but.
I think he had one guy set up at that end, and then he was set up at the other end, and I don't know,
And if it failed,
yeah.
if it failed, they wouldn't know about it until they got back together again, and then they go, oh man, all right, I guess we gotta do that again.
Alright, I gotta know now.
All right, while he's looking that up. So the mass of the person is just mass of the person, so we'll just write, be clever, m sub p. Now the mass of the Earth, if I want to figure out the mass of this part right here, when he's a distance r away, little r away, I know the density is the same. So the density of, I'll just put down little r, is the same as the density of big R. So just using the notation for the density of that small little hump there in the middle, it's got to be the same density as for the entire planet. Because we're assuming it's uniform, which means constant. So this is mass of that little part over the volume of that little part is equal to the mass of the entire planet over the volume of the entire planet. Now I'm trying to find mass of little r in order to plug into the formula, because I do need to know both masses. So mass of that, the small chunk there, m sub r, little r, is got to be, well, I'm solving for this, so I'll just multiply both sides by the volume there. So this becomes m big R times the volume of little r over the volume of big R. And so we're dealing with a sphere. I am assuming that it is a sphere. What is the volume of a sphere?
Oh, there's a one, no,
Yes, there is.
there's a 1/3 in there somewhere, or 1/4.
There is a 3 in the denominator,
2/3.
4/3.
Yeah, he put the sticks in two different cities.
How far apart?
It's not saying here, but
I was picturing like Alexandria and Cairo, but that could just be my imagination.
4/3 times 4. 4/3 times or to the third.
Yeah, 4/3 pi r cubed.
it's just saying that a geometric calculation reveals that the circumference of the Earth is the difference between the two cities divided by the difference in one shadow angles expressed as a fraction of one term.
Yeah, they always get to that. They never really talk about the conducting of the experiment really, other than 2 sticks far apart. And it's possible that it's lost to history and he made the whole thing up, but you get away with it if you're close to right.
And it was also 2,000 years ago, so.
Yeah.
He had no choice, it was here, would have been thrown.
All right, so now we've got mass of the planet. So what I'm labeling is m sub r here, just as in the mass for the, within the total radius, times 4/3 pi little r cubed over 4/3 times pi times big R cubed. And obviously you got some canceling out that goes on here. The 4/3 go away. And we can do it with some dramatic effect here with, there we go, that's as dramatic as we get. And so my force due to gravity is big G times mass of the person times mass of the part that's actually attracting them, in other words, the small part. So that's mass for the whole radius times r cubed over big R cubed divided by little r squared. I got 2 little r's on the bottom and 2 on the top that'll cancel out. And so ultimately the force due to gravity, this is the magnitude, not worrying about direction at the moment, we'll bring that in a second. But the magnitude of the force due to gravity is big G, mass of the planet, mass of the Earth, over big R cubed times little r. It is a linear relationship once you get inside the planet. Outside the planet, it's a 1 over r squared relationship. Inside the planet, it's proportional to just how far you are from the center. All right, questions to there before we actually connect it with what we've done?
I have a question.
Yes.
What's the difference between the big R and the little R?
Big R is the radius of the planet. Little r is how far he is away from the center. So he starts out, at the beginning, little r and big R are the same thing, but as soon as he steps in and starts falling, little r starts getting smaller. And then it gets to 0, and then little r starts getting bigger again. No other questions at the moment? Ultimately, this question stems from the question I got years ago of a student asking, so if you did have a hole all the way through the center of the earth and you jumped in, how long would it take you to get to the other side? We'll answer that.
Well, if the density wasn't uniform, wouldn't you never get to the other side? You stay in the middle.
No, what would keep you in the middle is if there was something basically taking energy away from you. So if there's air resistance, that would ultimately put you somewhere in the middle. Or if you're rubbing against the sides. So let's throw in no friction.
But isn't the density of the earth, isn't the core of the earth denser than the rest of it? So wouldn't it have less mass?
So what was the last bit?
Like, if the density wasn't uniform, wouldn't the person stay in the core because it's the densest part of the earth?
No, what would change is, as it is right now, there's a fairly predictable formula that we're gonna come up with, for what his acceleration and velocity would be. If we still have the spherical symmetry, but recognize the density is not the same, that means that his acceleration would be a little bit more erratic. But he'd still be going fastest in the middle, he'd go slingshot, because he's not going 0 at the middle. He would then start slowing down as soon as he passed the middle, and then he would stop when he gets to here again. But it would not change the fact that he didn't up here. The only thing that could change that is this.
Now, if he jumps through the hole, once he gets to the other side, is he gonna be on his head or his feet?
That would depend upon what he does. If he just jumps in like this, his feet would pop out the other end. He'd be basically upside down from their point of view, and then you go shooting back in.
I've asked this question for years. I've always wondered it.
Yeah, now, it is possible that he could turn himself around potentially.
Oh, yeah,
Let's see,
I'm
so if you're going down like that, if you ball up, ooh, actually, is it possible for it to turn around?
It would probably depend on the diameter of the hole.
Well, you assume it's big enough that he's not rubbing against the sides.
So like.
So he's nothing to push against.
Let's say it's like 10 meters.
holes.
So, in space, if you don't push, the films of astronauts floating around, whenever they do somersaults, don't they always push against the wall, don't they?
Yeah,
So if you can't push against anything, can you do a somersault in space?
but
If you can do a somersault and you go skydiving.
Yeah, but you got air there.
So we're assuming there's no air, there's nothing, just a
Yeah,
void.
but when skydiving, if there's no air,
Yeah, I guess you
Well-
use the air resistance to flip yourself.
yeah,
Whatever it
that's
is.
what I'm wondering now.
no, you couldn't move around if you didn't have air there.
All right, so you're falling like this, you just. Because you're starting out with no angular velocity, so you're falling down. I can change my angular momentum, but ultimately if I have no spin to begin with, I'm not convinced right now that you could turn yourself around without touching against something. We'd have to throw in, he can push against the wall, but there's no friction there. But then,
If you can't move left or right, you can't get to the wall and push off of.
yeah,
Sounds like we need to dig a hole.
Ah.
This is gonna be our second lab.
wonder what the school would say. The trouble is that despite the legends that, you dig through to China, you could actually dig through to someplace in the Pacific Ocean, and you would just drain it. I mean, you'd cool down the Earth's core, and I think bad things would happen.
There's only a couple places that if you drill on one side of the hole, or on one side of the earth and you end up on the other side, there'd be land there. There's only a couple places on earth like that.
I can believe that. All right, anyway, back to the problem. Yeah, so if you can't turn around, your feet would pop up first. All right, so let's now deal with direction. I know Newton's second law, F equals ma. The force, well, if I'm here, so the radial direction, so we indicate the direction with, if I've got some sort of spherical symmetry, usually with something like r hat. R hat is called a radial unit vector. And it's with I hat, j hat, k hat. I'm assuming this doesn't use I, j, and k for the unit vectors, as opposed to x, y, and z.
I don't remember.
Okay. Unit vector. What's a unit vector?
A line of the direction.
Okay. It's a vector, first off. If it's a vector, what are the two things it has to have?
Magnitude and direction.
All right, so what is the magnitude of a unit vector?
The length of the line.
No,
Displacement.
you're going way more complicated than you need to. And it's not zero, by the way. Okay, the hint is the name, unit vector. What is the magnitude of a unit vector?
It's deceleration.
The number. The number.
What number?
The number of the vector, or just the unit.
Number of units.
Okay, I see where you're coming from on that one. Not the right interpretation of it. Again, my reading skills off today. Let's see if we can work on that. I know it's been a week off. Unit 1. A unit vector is a magnitude of 1. The direction for I hat, j hat, and k hat, I hat, j hat, k hat, is what you say it is.
Actually, right, I think we use X, Y, Z